Hello, welcome to this clip going through the Cambridge Chemistry Challenge 2019 paper. I'll do question 1 on this clip, and there'll be a separate clip for question 2. So as in all the clips I do for Cambridge Chemistry Challenge, it's worth taking a couple of moments to have a look at what they actually mean by the instructions on the front of the paper. So the paper is designed to foster resilience, but in a low-threat type of way. So basically you're free to explore some lines of thought and problem-solving techniques that you might feel are risky in an A-level exam, but in a funny kind of way that toughens you up for an A-level exam, doesn't it? Because it means that your mind is a bit more loosened up when you come back to an A-level later on. So timings are similar to A-levels in terms of marks per minute, approximately 1.3 minutes per mark. And when you use significant figures, go for the least sensitive in the question. That's what they mean by an appropriate number of significant figures. Or if you're not sure, 3 significant figures is a good starting point. And it goes without saying that units are very important, because the paper will try and stretch your ability to convert between very high or very low orders of magnitude. So you'll find yourself dealing with very large or very small numbers in your calculator. Don't be put off by this. This is deliberate, so that it makes sure that you follow the courage of your own convictions and have confidence in your mathematical skills and see them through to the end. So the periodic table that you get with your C3L6 paper will have relative atomic mass values to 2 decimal places in most cases, as you can see, as opposed to in 1 decimal place, which is what you tend to get in exam board periodic tables. So use the data that's here in your periodic table you get with the paper, rather than values you might have recalled or remembered from just repeatedly using the normal periodic table you get in A-level questions. So the calculations will expect you to use the 2 decimal place values for the relative atomic mass. So each Cambridge Chemistry Challenge question will always start with some general information that will set the context of the question. In this case, it's obviously the history of the periodic table. So it's always worth having a read of this in case there's some key information or data perhaps contained inside it that might help you a bit later. So what it does this time is it signals obviously that 2019 is the 150th anniversary of the publication of Dmitry Mendeleev's first draft of his periodic table, which they've shown you a picture of. And although it was quite a feat at the time, it was quite incredible the way he was able to predict the positions of elements that we hadn't even discovered yet. There were some mistakes. Just like a first draft of anything, there would be some mistakes in it, as you'd expect. So the first section, which is question A and B, or section A and B, talks about the atomic mass of indium. So let's have a look at part A. So the very first part of the question talks about indium metal being dissolved in acid, and the resulting solution was reacted with sodium hydroxide sodium hydroxide solution to precipitate out indium hydroxide. Now the indium hydroxide can be filtered out because it's a precipitate, and then that can be heated to form IN2O3, one of the oxides of indium. So the first thing they want is the oxidation state. So if we take IN2O3 and we look at the oxygen, it's -2, so therefore 3 of them. So that makes a total contribution of -6 to the overall oxidation number of the compound, which will be 0, obviously. So for indium, there's 2 of them, so that must mean that indium is +3. So in part 2 it says, in dilute mineral acids, indium metal slowly reacts and gives out a flammable gas. Obviously, if you think back to GCSE and before that, you'll know that metals react with acids to give hydrogen. So that allows us to construct an equation between indium metal and dilute nitric acid. So I've left a bit of space for adding the balancing numbers in. So remembering that the nitrate ion is -1, so in HNO3, if NO3 is -1, then hydrogen will be +1. Any uncombined elements are obviously going to be 0. So first of all, if you remember that the indium is in oxidation state +3 when it forms compounds in this particular question. So that means I need 3 nitrates, so hence 3 HNO3s, which gives me 1.5 hydrogens. So if we add the oxidation numbers in as well, we can quickly work out what's been oxidized and what's been reduced. So if the oxidation number goes up, it's been oxidized. If the oxidation number goes down, it's been reduced. So we can say that indium has been oxidized from 0 in indium metal to +3 in indium nitrate, and hydrogen is reduced from +1 in nitric acid to 0 in hydrogen. So if we now concentrate our minds on part 4, where it says, with hot nitric acid or with more concentrated nitric acid, the only gases formed are oxides of nitrogen, and they want the equation for the reaction of indium metal with nitric acid forming nitric oxide. So with this one, you can assume that you have the same oxidation state as before. For indium, as there's no suggestion that it adopts another oxidation state. So they give you the equation, or they give you the reactants and products, and you've got indium nitrate, you've got nitrogen monoxide as the only gas, so we can use the hydrogen to make water this time instead of H2 gas. So we can start thinking about the balancing numbers. So now we need to think about how to make this work. You need at least 3 HNO3s to produce the indium nitrate, but there's also another nitrogen required, so there's actually 4 nitrogens on the right hand side. So that means we have to put 4 HNO3s on the left hand side. Now if we've got 4 hydrogens on the left hand side at this point, that means we need 2 waters on the right hand side to balance that out. So in part V, it says, give the equation for the formation of indium hydroxide from aqueous indium nitrate and sodium hydroxide. So there's a little bit less information this time, so a bit more thinking needed. So again, leaving space for balancing numbers. So maintaining the same oxidation state, we know that we get indium 3 hydroxide, so 3 sodium hydroxides needed, and also 3 sodium nitrates produced as the side product. So in the question, it says that the indium hydroxide is then heated to form indium oxide. So it's quite easy now to put the equation together, because you're breaking something up in a decomposition into 2 or more smaller compounds. So the decomposition is simply indium hydroxide turning into indium oxide plus something else. So the hydrogen in the hydroxide has to go somewhere, and hydrogen really does one of only a few things. The main thing it does most of the time in chemistry is turn into water. So from this, we can now see that we have to work out, using the modern atomic mass of indium, calculate the maximum mass of indium oxide that could be formed from 1 gram of indium metal. So sorry, I forgot to put in the balancing numbers there, because I obviously hadn't balanced my indium out. So looking at that last bit, I need to clear the screen slightly to make some space to do our calculation. So I'm going to get rid of some of the wordy bits and leave the equations so we can use them to work it out. Now I also need to get the modern atomic mass of indium, which suggests I need to go to the periodic table from the paper, which is I'll get to the little cell for indium from that and pop it on here as well. So looking at the equations, you can see that you can use mole ratios, and the mole ratio of indium to indium oxide is 2 to 1. So the molar mass of indium oxide is 277.64 grams per mole. So not forgetting the molar mass of the indium itself, we can now work out that the moles of indium in 1 gram is moles equals mass over mR, obviously. It gives you 8.709284097 times 10 to the minus 3 moles using my calculator value, which, using the stoichiometry, I can have that to get the number of moles of indium oxide, and multiplying that by the molar mass, which is 277.64, we get 1.21 grams of indium oxide. So for part B, it mentions that Mendeleev created his first table at the time that indium had only just been discovered, and its chemical properties weren't fully known at that point. And the error in the mass that they mentioned earlier in the question came from the fact that the correct formula for indium oxide, e.g. In2O3, was not actually known at the time. So therefore, the question wants you to work out two formulae. So it says 0.5135 grams of indium metal was converted to 0.6243 grams of the oxide. And it says, using these data and the modern relative atomic mass of oxygen, calculate the apparent atomic mass of indium, assuming these two formulae. Okay, so looking at the two different formulae, I need to leave two different bits of space to do my calculations. So the first thing to do is to look at the data I've been given. I've got 0.5135 grams of indium metal and 0.6243 grams of the oxide. So I've got to work out how much oxygen I've taken up to make the indium oxide. So the difference is 0.1108, and to get the relative atomic mass of the indium, I take the relative atomic mass of an oxygen atom, or 1 mole of oxygen atoms, that is, sorry, and multiply that by the stoichiometric ratio. So it's 1-to-1 ratio this time. So you look at 0.5135 divided by 0.1108, and you multiply that by 16 to give you 74.2. And in the second one, because you're looking at 2 oxygens per indium oxide, you do the same thing but multiply it by 32. So this gives us 148.3 grams per mole if the oxide is InO2. So we can now go on to the next question, next part. So this next bit gets a little bit easier because a bit of thinking was required for that last part. So what they want is how many protons, neutrons and electrons does an iodide ion contain? So the box from the periodic table tells us already that we've got 53 protons. Now obviously, just taking 126.90, you can't get 0.9 of a neutron. So the question tells us that we can consider this to be 127. So therefore, if we take it to be 127, then the neutrons are going to be the difference between 127 and 53. So not forgetting it's an iodide ion, I minus, that means the protons and the electrons are one different to each other. So be careful here because it's an iodide ion thereafter, not a iodine atom. So therefore the protons and the electrons will be slightly different. So I minus will have an extra electron because it's a negative charge, and as such you'd have 54 electrons instead of 53. So in the next question, it's not quite so straightforward here. We're looking at tellurium-30, and they want you to work out the percentage of tellurium-130 present in naturally occurring tellurium. And a little bit further up you can see that naturally occurring tellurium is a mix of 8 different isotopes whose proportions can vary depending on the sample. So this is a more complicated mathematical exercise here. So to simplify it, because it's a percentage we want, the percentages, or the combined percentages, always add up to 100. So let's make the percentages add up to 1 to make it a little bit easier. So it says that the heaviest of the isotopes found in naturally occurring tellurium is tellurium-130, which has a relative mass of 129.906223, and technically tellurium-30 is very slightly radioactive, and if there's none present, the relative atomic mass of tellurium would be 126.412449. So the 126.412449 can represent all the other tellurium isotopes, the fraction of the naturally occurring tellurium that they represent. So you multiply that by X. Now the tellurium 130, you multiply that by Y, and you add those two terms together to give you 127.60. So now we have an expression that will allow us to work out X and Y. So if you subtract the value that's associated with X, as in the other fraction, not the tellurium-130 part, away from both the relative atomic mass that we know and also the relative mass of tellurium-130, that gives you 33.99, or sorry, 0.3399, which is 33.99%. So for part E, now into the third section talking about thallium, it gives you a bit of information about where Mendeleev originally placed thallium. Now thallium is very poisonous, it's next to lead in the periodic table. I'm just checking. Yeah, it is to the left of lead. So that means that it's going to have similar properties and therefore similar effects on the body. So not particularly nice stuff to get inside you if you can avoid it. And it says it was misplaced with the elements from group 1 rather than the elements in group 13, or in older style we'd call it the elements in group 3. So aluminium's group, in other words. So it says thallium can form salts in the +3 oxidation state like the other members of its group, but the 3+ ions are oxidizing, therefore they act as oxidizing agents. And in doing so they get reduced back down to oxidation state +1, like it says. And an example might be adding iodide ions to solutions of thallium 3+, giving a precipitate of thallium 1 iodide. So it says, give the equation for the reaction of aqueous thallium 3 nitrate with potassium iodide. So it's highly probable that the fact they're mentioning oxidation number changes, or oxidation, it might be an idea to try and use oxidation states to help you construct your equation. So we did a bit of work on indium earlier, which is above thallium in the periodic table. So it should be no surprise to realise that the nitrate of thallium is very similar in its stoichiometric mole ratios to the nitrate of indium, so TONO3. So we put in the potassium iodide, we put in the thallium 1 iodide, and noticing that it's a simple swap, a displacement as well as a redox, we can assume that you've got potassium nitrate on the right hand side as well. So +3 to +1 is a reduction with 2 electrons gained, and on the oxidation side there's 1 electron lost. But notice we haven't done anything about the balancing numbers yet. We've got 3 nitrates on the left, so we need 3 nitrates on the right. In front of, we have a 3 in front of KNO3, and also when you do that we'll need a 3 in front of Ki. But if there's 2 electrons being gained and 1 electron being lost twice, how come we're using 3? It's because one of the iodines is not actually oxidized or reduced. So 2 iodines reduced and 1 iodine stays the same. So it asks for the oxidation state of cesium in cesium iodide. Now cesium is group 1. Group 1 only ever give +1 oxidation states. So it says in the question that the most stable oxidation state of thallium is +1. We've already worked out that cesium is +1. So therefore the oxidation state of iodine must be a third, the average oxidation state. Notice they said average oxidation state, not actual oxidation state. So this is designed to throw you a little bit. So let's try the dot cross diagram in III. Now I think they've been a little bit cheeky here because they've called it part III. And if you think really carefully, how can you get an anion that has -1 in it to match the +1 of cesium and thallium? But it's got 3 iodines. III. Get it? I'll show you. So it's basically a linear anion with 3 covalently bonded iodines. It's got an overall -1 charge, so the average oxidation state of the iodine must be a third. Not the actual oxidation state, the average oxidation state. And then you've got a bond angle, obviously, of 180. Okay, so let's move on to part G. It's looking at the second draft of his table, Mendeleev's table. And it says that in question, all the elements in Mendeleev group 5, including nitrogen and niobium, form oxides with the elements in the +5 oxidation state. So this time it's getting easy again. So this shouldn't be too difficult to work out as the element 2 of the element and 5 of oxygen, so N2O5 and Nb2O5. So the second one asks us for a structure for a molecule of nitrogen 5 oxide. To work this out, you've got to start by thinking about what the +5 oxidation state means. It means that you've got 5 valence electrons involved in the bonding. So that's one possible structure. So to support this idea, some of the bonds highlighted might be dative covalent, with 2 electrons donated from nitrogen to oxygen. So as a result, you could also do that structure that I've drawn at the bottom of the screen. In the next part, they say that solid nitrogen 5 oxide has a different structure from the gaseous form and consists of linear cations. So here you have to think about how the N2O5 structure could be divided into 2 oppositely charged ions. So we looked at nitrate ions earlier on, or we were thinking about them earlier on when we were doing some equation balancing. You should be familiar with the nitrate ion, so that could be a starting point. And if you happen to have done any aromatics work, you'll have come across the nitration of benzene. And it's our old friend the electrophile, the nitroelectrophile, so NO2+, nitronium ion. So it's now time for a Hesse cycle, and we can tell this because we've got enthalpy data to deal with. So let's start by putting the equation in for the reaction we're supposed to be working out, delta RH for. And because it's enthalpy of formation data we're given, we put the elements in their correct mole ratios at the bottom. Now we know the enthalpy of formation of N2O5, so we can put that in. So to use this energy cycle and the data we're given, it's slightly cheeky because we haven't actually got the formation enthalpy for NO2. But we do have a formation enthalpy from nitrogen monoxide, rather than from its original elements. So the first stage is to break the nitrogen molecules up into 4 individual nitrogen atoms. Now at the same time, I need to create 4 oxygen atoms from my 5 O2s. So I take 2 O2, so that's 2 lots of 498, to make 4 oxygens, and I already have 4 nitrogens, so I have the ingredients to make 4 lots of nitrogen monoxide, from which I can go on to make 4 lots of nitrogen dioxide. So, while we're doing this, obviously what I'm going to be doing a little bit later on is adding all this together. So I've made my 4 nitrogen monoxides. I can go on now and turn them into 4 NO2s. I've got an equation for that process. And what I've got to do, first of all, is to take the NO and look at what I have to do with it. I have to go from NO to NO2. So 4 of them involves 3 O2s. So 4 NO plus 3 O2 gives you 4 NO2. Now you have an O2 spare, that's what the O2 is up in the black equation. So I actually use up 2 O2s, but because I'm not breaking nitrogen oxygen bonds, I'm making them, I use minus 631, not positive 631. I've also got the formation enthalpy of minus 58.1 that I need to use, and there's 4 of those, so that's 4 times minus 58.1. So that gives me 107, plus 107 kilojoules per mole to the minus 1. So 2 different lithium niobate 5 salts exist. The niobate 5 part means that the niobium in the niobate ion is plus 5. So they've described 2 reactions there, and I've given you the equations for those 2 reactions. And in red I've highlighted the lithium salt that is formed in each case. So in the same way that H2O is an analogue of H2S, or CO2 could be analogous to CS2, carbon disulfide. What they mean by analogues here is that the arrangement, the mole ratio rather, of the atoms, etc., inside the salt are the same as LiNO3, except you take out the N and put in Nb. And likewise for Li3PO4, you take out the P and put in Nb. So that gives you LiNbO3 and Li3NbO4. So throughout this part, I'll be using information from the blue box. I've put a little blue line around the section that gives the information that you need to use. So it asks you to give the full electron configurations of calcium and zinc in S, P and D notation. So this first part should be quite straightforward. Then it says, given the maximum oxidation states of elements in group 2 and in group 12 are +2, what are the valence electrons of barium and mercury? So in group 2, for example, we know that the outer shell electrons are in the s orbital at energy level. So if we look at the periodic table and we find barium and mercury, they're in period 6, so it must be 6s2. It's going to be 4s2 3d5 for manganese and 4s2 4p5 for bromine. Okay, so now what we need to do is look closely at use the periodic table to write down the full electron configuration of ognanoson, the last element of the periodic table. So remembering that the quantum number in D block is 1 less than the period, so period 7 will have 6 D configurations. So remembering that the quantum number in D block is 1 less than the period number, so period 7 will have 6 D configurations. So if we take the circled element, Cn, that should end in 6D. So working back from ognanoson, I'm going to build up the electron configuration bit by bit. So taking us to zinc, that should be fairly familiar. So now we're at barium, so we drop down to the lanthanoids and we start incorporating F block. And when we get to the end of an F block, we go back up to periods 6 or 7. So we just count the atomic numbers all the way across. So going from 70 at ytterbium back to 71 at lutetium, for example. And that eventually takes it to ognanoson. That in order to complete the next row of the periodic table, starting with electrons in the 8s shell, you need to start filling elements in the first row of the G block. Now let's work out how many 5G orbitals will need to be filled. So to do this, we need to have a little bit of logic. So for 8s, the principal quantum number is 8, but the G orbitals that would go with that, the G subshell that would go alongside that, would mean an element in groups 3 to 12. And it says in the elements for groups 3 to 12, the electrons are filling d orbitals in shells with principal quantum numbers 1 less than the period. So the principal quantum number, so a G subshell has to contain 4 more electrons than an F subshell. So if an F subshell contains 4 more than a D subshell, 14 plus 4 makes 18 electrons, so that's 9 orbitals in a G subshell. So for the element beneath ognanoson, sorry, I've been pronouncing it wrong all this time, you need to add 50 electrons. So 2 for an S orbital, 18 for G subshell, 14 for an F subshell, 10 for a D subshell, and 6 for a P subshell. So that would give it 168 grams per mole. So, we're at the end of the clip now. It's been a bit of a tough one, but if you've got this far, thanks for listening. Until next time, see you soon.